Okay, hello everyone. Welcome to our third Ukraine seminar in fundamental physics. Thanks to all of you for joining us. Today we have a very interesting talk by Valerie Domcke from CERN. Valerie conducts research at the interface of particle physics and cosmology, covering a quite impressive range of topics spanning from particle physics, from problems of baryon asymmetry of the universe, dark matter, to gravitational wave physics. And she is a world-recognized expert in these fields. So let me say a few more words about our speaker. She studied theoretical physics at Technical University of München from 2005 to 2010. She wrote her master's thesis in the Max Planck Institute of Munich. Then she did her PhD in the field of theoretical cosmology and elementary particle physics under the supervision of Wilfried Buchmüller in DAISY. This is German electron synchrotron. And she got her PhD in 2013. Then she had two postdoc positions. One is CISA in Trieste, Italy, and another in the Université Paris-Diderot in Paris, in France. In 2017, she got a junior faculty position at DAISY. And finally, at 2020, she got a junior faculty position at Theory Division of CERN. And then she had a temporarily joint position CERN and EPFL in Lausanne, but now she is junior faculty position at CERN. And in her talk, Valerie Domcke, since 2018, I forgot to say that. In 2018, she was elected to Die Junge Academy, which is the Young Scientists Academy of Germany. And today, in her talk, Valerie will tell us about how to detect high-frequency gravitational waves with some techniques which were created for different purposes, but how to adapt those techniques to detect high-frequency gravitational waves. First of all, I would like to thank you, Valerie, for agreeing to give a talk today, and the floor is yours.
Thanks, Sasha. Thanks for the very nice introduction. I mean, at the beginning of the talk, one always say thanks to the organizers, blah, blah, for inviting and so on. So thank you, right? But the difference this time is that I actually mean it, right? So really, it's an honor to be here today and to give this talk in this young but I think important seminar series. So I will talk about how to use methods from particle physics to look for high-frequency gravitational waves. I will explain a bit why I think that's an interesting question, what is the motivation, and then how these techniques work. And I mean, I know it's always a bit hard on Zoom, but I also encourage you, if you do have questions along the talk, don't hesitate to interrupt me. Okay. And this is work based on the one part based on this living review, which is an output of the Ultra High Frequency Gravitational Wave Initiative, and work with my collaborators Camillo, Sonmuk, and Nick, some of which will appear hopefully very soon. So this is the plan. In the first part of the talk, I will talk about why I think gravitational waves in the high frequency, where high frequency means megahertz to terahertz, is something interesting to look for. For context, all the existing gravitational wave experiments, meaning pulsar timing arrays, LIGO, Virgo, but also future experiments such as the Einstein telescope or LISA, they are all in lower frequency range. They range from nanohertz to about kilohertz. So now we're going higher frequencies, and I'll explain why I think that's interesting. And then in the second part, I will talk about, well, basically I will be talking about electromagnetism in curved spacetime, because a gravitational wave is in the end just that. It's a perturbation of spacetime, and I will show how experiments such as this one shown here, which was initially built for looking for axion particles, how they can be repurposed or even recasted to look for gravitational waves. So, okay, why do we care about high-frequency gravitational waves and what sources could there be. So I'd like to distinguish between what I call cosmological sources and astrophysical sources. So cosmological sources means some violent event in the very early universe. Early universe means high energies, means we don't know what particle physics model applies at these high energies. It's out of the range that we can test with colliders and that we will likely ever be able to test with colliders. So there's a whole range of models explaining what sort of particle physics could be going on at these high temperatures, some of which predict violent processes such as phase transitions, or topological defects, and these could source gravitational waves, which would then be at these high frequencies. A cosmological background is typically what we call a stochastic background, meaning it's isotropic, it's stationary, it contains superposition of all sorts of frequencies. It really seems like white noise, or roughly white noise in your detector. There's roughly a one-to-one relation, I'll come to that on the next slide, between the time when such an event happened in the history of the universe and the frequency at which we observe it today, whereby earlier times correspond to higher frequencies. And that's one reason to look for gravitational waves at such high frequencies. So far, we know very little about gravitational waves in this frequency range. The only thing that we have, and I'll come back to that in a second, is that we do have a bound. We don't want too much radiation or too much energy in gravitational waves to the point that they would change the equation of state of the universe. I should, however, also say that in vanilla cosmology, so if you write down the absolute simplest model of early universe cosmology, you get sources of these high-frequency gravitational waves, but they are so weak that we're not going to see them in any foreseeable future. But as I said, there's many possible extensions, well motivated for their purposes, which do give you signals, meaning if you probe this region, you are constraining particle physics models at high energy. On the astrophysical side, it's a different type of source that you would be looking for. You would be looking for localized gravitational wave sources. I'll give you an example in a minute. Also here, I should stress that there's no known astrophysical objects in the sense of observed astrophysical objects that are compact enough and small enough that they would give gravitational waves at these high frequencies, simply because the wavelength basically has to correspond to the size of the object or the distance between the two objects, and going to high frequencies means going to very small objects. And then they tend to be too light to source an appreciable amount of gravitational waves. There are, however, again, in models beyond the standard model of particle physics, there are exotic objects which people discuss, such as, for example, primordial black holes, and these would give signals in this frequency range. So again, looking for gravitational waves at these high frequencies is looking for new physics, is looking for extensions beyond the standard model of particle physics that we have at the moment, which for me as a particle physics theorist, as a cosmologist, is exactly the reason why to do it. Of course, if you're an experimentalist, this is not very good news because it means you have no verification signals, you have no guaranteed sources. On the other hand, it's a background-free search of new physics in some sense. So I just want to spend one slide on some facts about the cosmological sources and one slide on the astrophysical sources. So for the cosmological sources, I mentioned already that there's an upper bound, which simply comes from the total amount of energy density that we can tolerate in gravitational waves. So what you have here is the energy density in gravitational waves with respect to the total energy density in the universe. And that is constrained to be a fraction of the radiation energy density today. Namely, it cannot be more than 10% of the radiation energy density today, or cannot be more than 10% of the total energy budget at very early times when the universe was radiation dominated. Because otherwise, it would just really, at leading order, change the expansion history of the universe, And then a lot of the cosmological probes that we have would have detected this. So that's the constraint that we have. And we can roughly translate this constraint on the energy density to a constraint on the characteristic strain, which is roughly the amplitude of the gravitational waves. And at, say, 100 megahertz, which will be roughly the frequencies we will be working at, this delta N effective is something like 0.1. So the strain sensitivity that we need to reach to actually probe cosmological sources is of the order of 10 to minus 30. For comparison, LIGO reaches something like 10 to minus 24, but again, at a different frequency range. I mentioned that there's a relation between the frequency at which we observe the gravitational wave and the energy of the event, or the temperature of the event, which is given by this relation here, where this just comes from saying I have an event in cosmological history that happened at a given time, and the typical scale of this event is some fraction, epsilon, of the Hubble horizon at that time. And then you just redshift everything to today, and you'll find this relation between the frequency today and the temperature at which this event took place, or the energy of this event. As 10 to the 15 JeV is a reference scale, which is roughly the scale of grand unification. So where all the standard model gauge groups unified, well, possibly unified into a single group, which is a scale where we expect, or one of the scales where we expect new physics to happen. Similarly, for the experts, you can also, if you're not in a radiation area, if you're in an inflation area, you're not going to measure time in terms of temperature, but in terms of e-folds. But again, there's a roughly a one-to-one relation. In this case, high frequencies corresponds to perturbations which exit the horizon just before the end of inflation. And yeah, there's a ton of examples, right? This could be a completely separate talk. But it's not difficult on the model building side to come up with ideas which are sound, theoretically consistent, motivated because they address other problems in particle physics and cosmology, and which actually saturate this observational bound. So as soon as we become better in this, we're really probing into this parameter space of models that are out there, and we learn something interesting. Now, on the astrophysical side, right, this is a bit different, right? Because now we're talking about, for example, some merger of some compact objects, or for example, mergers of primordial black holes. This would be a signal that looks very much like the type of signals that we've seen in LIGO. So a typical chirp signal where you first observe the in-spiral phase, and then towards the end, towards the merger, you really see kind of an increase in frequency and amplitude of the signal. Just the entire thing shifted to higher frequencies compared to LIGO because we're looking at smaller objects, which is why they need to be, cannot be black holes generated from the collapse of stars, but would need to be black holes generated by some other means. So these give you an event which is transient. So it comes from a localized region in the sky. You observe the signal for some amount of time, typically very short, and then it's gone again. So the contribution of this to the overall energy density of the universe is negligible. So the bound we discussed on the previous slide on the amplitude does not apply, but it's a completely different type of search that you would do. You would look for these transient signals. So the penalty factor is they're very short, so you have less time to detect them. The advantage is the amplitude. If you're lucky, the thing is close by, the amplitude can be much higher. So this is a pretty busy plot, but basically what we try to do is estimate the amplitude that you can expect from such primordial black holes if they are a sizable fraction of dark matter. So this is, in some sense, this is the most optimistic assumption that you can make. And then if you make that assumption, then you can actually compute how many of these primordial black holes you have in the universe. You can compute how often they merge. You can compute the type of signals that they emit. And you can say, okay, if I want to see one event per year in my detector, what sort of a strain sensitivity does my detector need to have? And this is shown on this plot on the right. So here, for example, this curve here is the 1-year curve. So if I want to see one event per year, I need to build a detector, which is a strain sensitivity of something like 10 to minus 23, 10 to minus 24, which is already a lot easier than measuring the stochastic background, which, if you recall, was at more 10 to minus 30 level. This 10 to minus 23, 10 to minus 24 is the sensitivity that LIGO reaches. But again, LIGO reaches it at a lower frequency range. And as we'll see, it's not obvious or not easy to reach the same strain sensitivity at higher frequencies. And I should also stress that this is really this plot contains a bunch of assumptions. And this is, I think, the most optimistic plot you can make. So it should be taken with a grain of salt. This is just to indicate kind of which sensitivity you would need to reach to start to be able to say something interesting. Okay, so why haven't we done this yet, right? So why is this difficult? So this is the view of a theorist. So we plot on the axis the energy density as a function of the frequency, and as I said, the only constraint that we have is this observational constraint on the total energy density, which is a horizontal line in this parameter space. And then you can build lots and lots of fun models for very good reasons. And you particularly like these models at high frequency because here you are probing physics at scales beyond collider. So you can be very creative, you can have new ideas, and there's no experimental data to make your life difficult. So there's a whole bunch of models living in this range. Then you make the mistake of talking to an experimentalist. And the first thing that they tell you is that, well, that's not the way they normally do plots. They typically do plots like this, where on the axis, they're not putting the energy density, but they're putting the strain. So strain means the amplitude of the gravitational wave. Or in LIGO, for example, it means the relative change in the arm lengths. When the gravitational wave passes through a Michelson interferometer, it very slightly changes one arm length with respect to the other. And this very slight relative change is what is this strain, this characteristic strain. So with that in mind, if you plot in this parameter space, you take into account that the energy density scales as amplitude of the gravitational wave squared times frequency squared, you then see that this nice horizontal line here actually turns into a slippery slope, which means even if, say, imagine this is LIGO, right? Even if you manage to build a detector of a similar sensitivity of LIGO, in particular the stochastic sources, but in general all sources are kind of sliding away underneath you. So even if you reach the same relative strain sensitivity, you may still have a further distance from the models that you actually set out to probe. The other issue is that this is if you think in terms of LIGO, right, this is a relative distance measurement. So for LIGO, this is basically they measure the arm length of one of these arms, right, which is 4 kilometers, okay, times, say, a factor 1,000 for the cavity that they have inside. That's the arm length that they have. And on top of this arm length, they measure a distance change. And this distance change is the size of the proton radius. So that's an incredibly small distance, and that gives them this relative strain sensitivity of 10 to minus 24. Now, as you go to higher frequency, you would want to make the arm length of your detector smaller because you're probing something with a shorter wavelength. However, you would then correspondingly need to make this absolute distance measurement even more precise. And there's not much chance to measure anything more than the diameter of a proton. I mean, you just cannot make your mirror smooth enough to do that. So this is why there's two challenges here. So one is, okay, the sources are kind of sliding out underneath you. And B is it's not at all trivial to go horizontally in experimental sensitivity in this plane. So these are the challenges. So we had a series of workshops starting in 2019, and there'll be a third one this year in December, if you're interested, with both in-person participation at CERN and online participation possible. And here we got together, theorists and experimentalists got together and kind of tried to assess, okay, what are the experimental concepts which are out there? And we're still in the process of trying to understand which one might be the most promising and how could this field move forward in the future. So a spoiler, none of the experimental concepts that are out there at the moment actually reach the sensitivity that we need to probe the cosmological sources, which is the ultimate motivation in this game. But there's been a huge amount of development just in the recent years. And new detector concepts have been popping out, and it's a very, very agile field. So I think the last word has not been said here yet. So we're still in the process of exploring various ideas. In particular, because here we're looking at, say, megahertz to gigahertz, right? This means in terms of wavelength, this means something like whatever, centimeters to meters. So that's the typical size that fits in a lab. So you're looking for something which fits in a lab, does an extremely precise measurement, and then you need to understand what is the sensitivity of this extremely precise measurement to a perturbation of space-time. That is the game that people are playing. And it's not clear at the moment what is the particular measurement that gives you the best sensitivity. So I want to present one idea here, one that I've worked on. But yeah, just to say that, and I'll have a part at the end, just to say that this is just part of a much broader effort to try and understand how gravitational waves in this frequency range could be detected. Are there any questions so far before I move on?
It depends how when you want to have question. I have one in the middle, short one. Considering the slide number 5. So this is the plot for events, for example, mergers. And did you compare it with microlensing data? Because as far as I know, there is an upper bound for such compact objects like primordial black holes. And isn't it how to say? Isn't it that even in the best scenario, the rate of detection is so small that it's very below the microlensing bound, so it might be too optimistic to expect to observe such events?
Yes, you're absolutely right. Yes, so I was kind of glossing over that a bit. So actually, so to do this plot, I need to assume what exactly is the fraction of black holes that contribute to dark matter. And I said something very vague, right? Like I said something, okay, we choose this such that it makes up a significant amount. So what we actually do is we saturate the microlensing limits. So we choose this FPBH here, so the abundance of the black holes, exactly such that it's just below the current microlensing bounds.
Oh, okay.
But this is one of the things that I mean, that I said, this is the maximally optimistic plot you can do.
Mm-hmm. Got it. Thank you.
Okay, then let's move on. So to understand this this idea of how to detect gravitational waves using the experiment I was showing on the previous slide. So maybe I should say how does this experiment works very briefly. I'll have a more schematic plot in a second. So what this does is you have this wire which coils around here, generates a magnetic field in this toroidal green thing. And then the idea of this experiment is that you look at the interaction of this magnetic field with a pseudoscalar particle called an axion. And that gives you an induced magnetic field, which you then look for with some pickup loop here, which is this silver ring in the middle. And that's this is just a toy demonstrator experiment, right? I mean, it's something like 10 centimeters big or so, very small. And this is to kind of demonstrate the concept in order to then scale this up to some bigger experiment. And here we want to see if this idea could also be interesting for looking for gravitational waves. So this is an experiment which already exists, and we can piggyback without needing any funding of our own. So in order to understand that, we need to understand how the gravitational wave interacts, well, how electrodynamics works in the presence of a gravitational wave. So a gravitational wave is just a small perturbation of the space-time. So what you need to do is you need to understand electromagnetism in curved space-time, and then just do an expansion to linear order in this small gravitational wave amplitude. Now, you would think that electromagnetism in curved spacetime is something super well known. And in fact, it is, right? In the sense that if you know what you're looking for, nearly everything is in Landau-Lifshitz. But of course, the notation is difficult. And so you compute it yourself. And then at the end, you assure yourself that what you've done is actually sensible. But there's some interesting lessons to learn here, which is why I want to spell this out. And that is the way the gravitational wave acts is that if I look at Maxwell's equations in the absence of external currents, so just imagine some block of electric or magnetic field, and we now look at the inside of this block of electric or magnetic field, then the usual Maxwell's equation, this is the homogeneous one, this is the inhomogeneous one, gets modified by the presence of an external effect, or no, I should say by the presence of an effective current. So something that is sourced by the gravitational wave, but enters Maxwell's equations in the same way as an external current would. And this effective current can be expressed in terms of an effective polarization and magnetization vector, which are given by these expressions here. And okay, there's a bunch of indices because this is complicated because the gravitational wave is spin 2. But the take-home message here is that each of these terms is linear in some component of the gravitational wave amplitude and is linear in the external electric or magnetic field. So the statement is, if you have some external electric or magnetic field that you apply in your lab, you have an incoming gravitational wave, then the combination of the two acts as an effective current in Maxwell's equation. And consequently, this effective current will act as a source term and induce small electric and magnetic fields. And in that sense, it is extremely similar to the axion. In the axion, you don't touch the metric, but you have an additional term in your Lagrangian where the axion couples to FF dual, or E times B. And also this you can express in terms of polarization and magnetization vectors. The structure is much simpler because there's no indices, because the axion is a pseudoscalar. But the structure is the same. Like you will have something. You have polarization and magnetization, which depends on the axion field, which is what you're looking for, and the external electrical magnetic field. And this is what gives us hope that with these types of axion experiments, we can actually also look for gravitational waves. Now, there's a subtlety here, which I don't want to dive into too much detail. But the subtlety here is that you have to be, I mean, you're working in GR, right? And in GR, you always have to be very careful with frames. So you need to make a frame choice and then stick to that frame choice throughout your computation. Or, of course, you can also do the computation. In principle, you can do the computation in a complete gauge invariant way the entire time. We will choose a frame. And the frame we will choose is the laboratory frame. So this is the frame in which the coordinates are really fixed by a hypothetical rigid ruler. And this is in particular different than the so-called transverse traceless frame that people normally use to describe gravitational waves. The reason we choose this frame is because this frame is much easier to describe the experimental setup. The price to pay is that the gravitational wave looks super messy. But okay, so these are the expressions, right? So they look messy, but I mean, they're still analytical functions, known analytical functions. So it's nothing that you can't deal with. But that just as a word of caution. Okay, so now how does this experiment work? So as I said, we have this toroidal static magnetic field. We then consider an incoming gravitational wave, which leads to an effective current. For the axion case, this effective current would exclusively also move around in this toroid. For the gravitational wave case, this effective current has all sorts of components going all over the place, but it also has a component which is running in the toroid. This is the one we will focus on. So now this effective current, the way it enters Maxwell's equation, it acts as a current. So it will induce a magnetic field, and you can just use the right-hand rule, right, to see that there will be a magnetic field coming up through the center of the loop, or through the center of the toroid. Now this is interesting, right, because in this idealized theorist point of view, we didn't have any external magnetic field in the center, right? The external magnetic field was only in the orange region. So we're now getting an induced field in a region where in principle there was no external field. Now, of course, in reality, there's going to be more complicated. You're going to have leakage of the external field also into the regions where it's not supposed to be. But recall that the external field is static, whereas this induced field will be oscillating with the frequency of the gravitational wave because it's induced by the gravitational wave. So it's pretty easy. I mean, just do a Fourier transform, right? It's pretty easy to distinguish an oscillating field from a static background. So this tiny oscillating field is something that you can look for. And in fact, it's exactly the same thing that the people look for when they perform the experiment for axions. So you can compute with the expressions I gave you in the previous slide. You can compute the magnitude of this flux, which flows through some pickup loop, which is given by this expression here. So this is the flux of the magnetic field through this loop. And it scales notably linear in the gravitational wave amplitude. It oscillates, as I said, with the frequency of the gravitational wave omega. It is proportional, of course, to the external magnetic field. This is what we saw already in this induced current expression. And it will scale as omega cubed, so frequency cubed, times the length scale of the detector to power 5. Now, we don't. This is the theory calculation, right? Now, what we actually, of course, want to know is how well can we measure this flux? And for that, in principle, you need to understand all the details of your detector. However, as I said, the thing that we're looking for here is really pretty much exactly the same thing that they're looking for the axions. So if you look at the flux that the axion induces, you get this expression here, which really looks very similar. You get the same oscillation factor. Now, instead of the gravitational wave amplitude, you have the coupling of the axion to electromagnetism, and you have, again, the external B field and, okay, some other volume factors at the end. But we can now, what we will do is we will just recast without having to understand exactly the level to which they can detect this magnetic flux. We can just recast the existing bounds on this parameter as bounds on this parameter by just equating the two fluxes. There's a bit of a caveat here because the signals can have different coherence and different durations, the axion signal and the gravitational wave signal. So when I say you just equate the fluxes, right, you need to take these different timescales into account. But this can be done without kind of having to dive too deep into all the subtleties of the detector setup. And so this is what we will do, right? We will compare, like, equate the two fluxes and then recast the axion bounds as gravitational wave bounds. Now, it's interesting to note that if you had just done dimensional analysis, you would have said that this should have scaled as gravitational wave amplitude times B0 just times R cubed, R square, or length of the instrument square. You would have not gotten this omega L to the cube factor. So we were wondering for quite a while, and this, like, typically you're doing this in a quasi-static regime. So omega times L is much smaller than 1. So it's a suppression factor. And so we were wondering, where's the suppression factor coming from? And at least one factor, okay, two powers of this, the suppression factor are just, okay, this is just the way GR works. It's just basically reflecting the fact that locally, you can always make the metric flat. And this is what kind of kills the omega 0 and omega 1 term. And then the omega squared term is killed by the cylindrical symmetry of the setup. But this is something you can very easily avoid because you can actually modify this loop in the center. Like before, we had a circular loop. Now I just take one half of the circle and twist it the other way around to get this figure 8 configuration. And now I'm breaking the cylindrical symmetry of my setup. And I can parametrically enhance my flux. Now I get a flux which scales as omega squared instead of omega cubed. So what's happening here is that the full flux, this omega squared flux going through the center of this loop actually is a dipole structure. And if I integrate over the full circle, I'm just getting cancellation. But as soon as I break the cylindrical symmetry in the pickup loop, I can recover the leading order contribution, which was canceling beforehand. So and we've been in touch with in particular the people of Abracadabra. Of course, if you tell them they need to modify the magnetic field, they don't like that at all. But modifying the pickup loop is something surprisingly easy, right? If you remember this plot here, the pickup loop is really just this metal ring here. So now what they're actually doing is they are running the same experiment with a figure 8 pickup loop to show, just again, it's a prototype, it's a demonstrator to show that this actually works, right? And you can actually look for gravitational waves with this type of configuration, which gives you a bit of a boost in the sensitivity.
Sorry, can I ask a question on this?
Yeah.
But why actually omega squared is better than omega cubed? You're interested in the high frequency gravitational waves, then omega cubed should be better, or I'm wrong?
So the point is that all these axion experiments only have data and the limit that omega L is smaller than 1. The reason, okay, there's many reasons for that, right? But so for the axion, that's the regime which is better to search for. And as you approach omega L goes close to 1, all sorts of really complicated things happen, right? You have to worry about resonances, you have to worry about corrections to Biot-Savart law. So they don't go there. They're all in the quasi-static regime.
Yeah, I see. So they do not want to have resonance in their detector. Yeah, I see. Mm-hmm.
Right.
Yeah,
there are, however, other axion experiments that do exploit the resonances. So they're like these microwave cavities which operate on resonance. And there, in fact, this omega L factor is 1. So then by playing this sort of game, you would not get a parametric enhancement, right? You would just get a whatever an order 1 contribution.
Okay, thank you.
Yeah, thanks for the question. Okay, so with that, we can take the existing axion searches, which is mainly Abra and Shaft, which publish data bounds on GA gamma gamma as a function of frequency. And we can also take future proposals, in particular the dark matter radio proposal, which is a future proposal how you would kind of upscale these type of detectors, mainly by having a resonant instrument, which is a scanning search. But resonant here again is not that you have electromagnetic resonance, it's just that the circuit that you read, the LC circuit that you read is on resonance. And a bigger magnetic volume. That's basically how they plan to do that. And with that, their goal is to reach the QCD axion line, which is this yellow line. And this is the sensitivity that they think they could reach. So we will recast the existing bounds and we will recast the future prospects. And so this is what we get. So here we have strain as a function of frequency. These are the existing limits, which are absolutely horrible. I mean, with strain sensitivities of 10 to minus 4, remember we want to get to 10 to minus 30 or something. But again, it's just a demonstrator experiment. And then if we just take the dark matter radio program, don't change anything, right? No new pickup loop, nothing, right? Just assume they do what they're going to do. And we just when you're done, we take the data, we recast. This is what we think we could get. So we could get down to 10 to minus 18. And the reason that we get so much better is because we have this linked to the 5 scaling, right? So you pay the penalty factor once, right? This is an ugly suppression factor. But then as you increase your volume, right, you have very good volume scaling. And then you start getting into the regime, which is actually kind of interesting for gravitational wave searches. So here's this putting a bit into context. So now we use the figure 8 pickup loop. And we also show on the same plot other proposals or other experiments. Some of them exist, like the levitated sensors exist, the bulk acoustic wave devices exist, the holometer exists. Everything else is also at the level of proposals at the moment. And you can see, okay, we get, I don't know, everybody is now kind of, but all of these, basically at least half this plot was empty only 2 years ago. So this is all stuff that has happened very recently, and everybody is now reaching estimated future sensitivities of the order of 10 to minus 20, which is not quite yet there where we need to be for the astrophysical signals, but it's slowly getting there. Though, as I said, this curve is probably a bit too optimistic for various reasons. We're still a while away from a cosmological background, right? Because that would be a 10 to minus 30. So status is we're not there yet. We're still missing several orders of magnitude. But this also shows you that, I mean, what did we do, right? I mean, we used an existing experiment, and all we did is we thought about electromagnetism in curved spacetime. This is something that, you know, was, in hindsight, a very low-hanging fruit. So I think this just tells you that there could even be already the ideal experiment out there, or it could be very easy to build, relatively easy to build, and just people haven't fully thought through how a gravitational wave would impact various high-precision lab experiments. So that's a bit my message, is that yeah, this is a fun playground to do relatively basic physics. Well, I mean, GR is not so super basic, but in principle, it's super well understood. You can just make a mess of things, but do relatively basic physics and still have the potential of really probing processes in the extremely early universe. So this is where we currently stand. As I said, this is a plot of the cosmological sources all down here, or possible cosmological sources, all constrained by this BBN bound, which is this dotted black line. And this was the status after the first workshop. So this is the status about 2 years ago. So at the time, the solid blocks were the existing experiments, and the empty blocks are the proposals. And I would say, like, by now we have at least a factor 2 more proposals. Not so much factor 2 more experiments, right? Experiments take a lot longer to build than they take to propose. But we have at least a factor 2 more proposals, and now at least we don't have these ginormous gaps here anymore. Like there's proposals covering essentially the entire regime up to, let's say, a terahertz or so, and even beyond. So with that, I conclude. So my 2 messages are that gravitational waves at high frequencies are very difficult to detect, but they are potentially a unique probe into the very early universe. And they would be really a smoking gun of new physics. And then the one method that I presented to look for them was axion haloscopes. So experiments designed to look for the dark matter axion. And here we exploit that electrodynamics in a curved background. So gravitational wave electrodynamics has quite clear similarities with axion electrodynamics, and hence a lot of experiments designed to look for axions are actually, coincidentally, already looking for gravitational waves. Yeah, so we put some bounds, which for the moment, the existing bounds are not of interest to any cosmological models. But we think we can at least improve significantly the sensitivity with upcoming axion searches which are on the horizon anyway, and then how to bridge the last few orders of magnitude is still an open challenge. And with that, I'd like to thank you for your attention, and I'm happy to take any more questions.
Okay, thank you very much. Let's thank Valerie for a very nice talk. Okay, colleagues, please, do you have any questions? Just raise your hand or unmute yourself. Don't be shy, please.
I have one more question. So I can't understand how can we use it to detect astrophysical events, but how do you plan to detect cosmological distribution of gravitational waves? Because as far as I understand, there is no clear spatial resolution of the proposed detector. And yeah, so how do you plan to detect cosmological high frequency gravitational waves?
Right. No, that's an excellent question. So, okay, so for these guys, for the axion haloscopes, for the moment, I mean, you would need to do a completely different type of data analysis. You could not just recast the axion searches because you're looking for something fundamentally different.
Yeah, something transient.
Exactly. So what you would for the cosmological sources, what you would be looking for is essentially an unaccounted noise source in your detector. So you would be looking for an irreducible noise component, which you manage to convince yourself is not some other detector noise. Okay, so that's very difficult. So the way LIGO does it, for example, LIGO has two instruments and they cross-correlate the two instruments. And the idea is that most of the detector noise will be uncorrelated across the two LIGO sites, but the gravitational wave will be correlated. Even the stochastic background will be correlated. And this is how LIGO, for example, is looking for a stochastic background. The way, for example, pulsar timing arrays do it, again, it's completely different frequencies, right? It's low frequencies. They use the angular resolution, right? So, or in some sense, right? Because despite that the angular resolution isn't good, there's still a very distinct pattern for the gravitational wave, as opposed to most other sources. So these are the types of games that you would play here too, right? You will probably need more than one instrument, and you would play with having kind of different orientations of the two instruments. You would think about what is the best distance to have between the two instruments. But it would be much more tricky, I think, to look for a stochastic background than for transient. I should, however, also mention that, for example, these guys, so this is also an axion experiment. This is a so-called light shining through the wall experiment. So the way it works for axions is you have a high power laser, which you shoot into a magnetic field. In this magnetic field, the photon from the laser and the static magnetic field have a vertex which generates an axion. Then you shoot this high power laser just onto a wall. So if the photon cannot pass the wall, but if the photon has converted into an axion, it can pass through the wall, reconvert on the other side, where you have another magnetic field, and you get again a photon which you detect with a camera. So you're shooting a laser at a wall, and then you put a camera behind the wall and wait to a photon magically appear. And the same happens for gravitational waves, right? So for gravitational waves, you don't even need the first laser, but you could have a gravitational wave converting into a photon in the presence of the background field. And here, the experiment is really just counting photons at the end. So all you care is the energy density in the field, the energy density in the gravitational wave field. And you don't care if it's coherent. You don't really care if it's transient because you're integrating over time. So here you could really look for a stochastic background.
Thank you for your answer.
Okay, any other questions? I have one. Maybe someone else will generate a question, but let me now ask, what is the main factor which which limitates this type of detectors, because as you said, it is a very good scaling with the size. So if we just increase by 1 order of magnitude, then we can reach like several orders of magnitudes in sensitivity. Why it is complicated just to build a bigger detector, 10 times bigger?
Right. So I think it's the challenge of sustaining magnetic field, strong magnetic field over large volume. So this thing, right, this got meter cubed, right? This is called 50 liters, right, because it has 50 liters volume, and this is called meter cubed because it has meter cubed volume, right? And here in our fantasy world, right, we draw something which is 100 meter cubed volume, right? So meaning we've extended the size by whatever, a factor, well, 2/3 of 100, right? Yeah. Power 2/3 of 100. So yes, right. So in principle, exactly. In principle, you increase the volume, right, and you gain. But the challenge is sustaining such a strong magnetic field over a large volume. The other way you could go to increase in sensitivity, since a lot of these experiments are resonant, right? And they want to probe the QCD axion line, right? So they run at a certain frequency until they run all the way down to the QCD axion line, and then they switch to the next frequency bin and they run again until they reach the QCD axion line, then they stop and they run again and so on, right? Now, if we don't care about the QCD axion, we can just be at one frequency and just run, right? And in principle, we can go lower in amplitude. The limitation that we hit, at least for the transient signals, is that they won't stay in band very long. Because here we're talking about, say, gigahertz gravitational waves, right? So they're not going to stay coherent and in band for years, right? And more like, seconds is already optimistic, right? Because seconds is already a coherence factor of 10 to the 9. So that's going to be the challenge there for the transient sources. Of course, if you manage, this comes back to the previous question, right? If you're thinking of how to detect a stochastic background, right, with a resonant instrument, then in principle, you just gain with integration time. But of course, you gain with square root of time, right? So there's at some point you have to stop.
Yeah, okay, I see. Thank you very much. And maybe turning back to the physics, so these types of gravitational waves that you are interested in, they should probe physics in the end of inflation, right?
Right, end of inflation or in the radiation-dominated universe after inflation, right? Yeah, like phase transitions, topological defects. Here we had some examples, right? Preheating, oscillons, those types of processes.
So this gravitational wave production from axion inflation is also in this list, so should be somewhere.
Yes, it's this one. It's called inflation extra species, right? So yes, you can basically, you can max out, depends on exactly how you write your scalar potential, right? But I think you could basically max out the BBN bound all the way until the end of inflation. And these lines all cut off here in this somewhat idealized view, because this corresponds to the horizon size at the end of inflation, right? Assuming whatever high scale inflation, 60-fold and so on. Which is, so this is like roughly, what is this? Like this is 100 megahertz roughly. This is this scale. And then this scale here, which goes a bit higher, which goes to about 100 gigahertz, is thermal gravitational waves. So gravitational waves that are produced thermally in the thermal bath as just an additional species to be produced in a thermal bath. So there, the scale is not set by the horizon, but by the temperature at kind of this very high scale. So then you get to about 100 gigahertz. And realistically, I think that's about as high as you could go, because now you have the maximally smallest horizon. And I don't see how you could kind of sensibly have a scale which is much smaller than kind of the scales set by the temperature. So here we actually have experiments, but I don't think we have, at least no cosmological sources that I can think of.
I see. And these experiments, they are also axion based, yes?
Right, but the reason, this is also interesting, because the reason that these experiments are here, right, as I said, I mean, they shoot, these are light shining through the wall experiments, or they are helioscope experiments, right? So, which are essentially also light shining through the wall, just that you replace the laser with the sun. So there, of course, okay, you shoot the light on the wall, and then after the wall, you have a camera. And of course, the camera that you put, if you're looking for axions, is sensitive to the frequency of the laser or, the thermal spectrum of the sun, because that's where you expect the axion signal. Now, for the gravitation wave, we don't care at all about the laser. We can get rid of the laser, right? We don't need the laser. So the fact that we're sensitive to these frequencies here is simply because that's the CCD camera that they put for the axions. Now, there's been the proposal, and I think at least for ALPS, they're actually very seriously considering this, is to just add additional cameras on the detection side. Which, of course, you would never get an axion at that frequency, because where would it come from? But this is not a fundamental frequency limitation. This is really just because the type of CCD camera that is installed. But we can detect photons at all these frequencies. So in principle, you can draw, if you want, a proposal line, which is kind of a diagonal here, because they're measuring energy density. A diagonal here, and you could in principle cover all of that with the suitable camera in there.
Okay, yeah, I see. Thank you very much. Okay, so this kind of measurements could be complementary because we know that inflaton potential can be constrained only from CMB observations, but these constraints apply only at 60 or 50 e-folds from the end of inflation. And this method could be a complementary to that. Of course, if it reaches the desired sensitivity, then we can, in principle, constrain from gravitational waves the inflaton potential in the end of inflation. And just the combination of two could be a very powerful tool to conclude what is the inflaton potential, the true model of inflation.
Yeah, totally. Well, also indirectly, right? Because even before you reach this BBN bound, you're probing the parameter space of PBHs. And that in turn probes the scalar power spectrum at the corresponding scales.
But I mean, to produce primordial black holes, you need like sufficiently strong scalar power spectrum, and maybe not in each inflationary model you can reach this threshold to produce them.
But also to probe, like, if you just imagine you just have slower inflation, right? So you have the CMB, and then just whatever m squared phi squared, right? And then you compute the gravitational wave signal. It's very small, right? It's not even on this plot, right? But it's going to be way below the BBN.
Below. Yeah, so these are some interesting phenomena, some maybe this axion inflation, for example, or some special features in the potential which would induce some strong gravitational wave production. Yeah, so then maybe it can be accompanied by this PBH production, and this can be indirectly seen. Okay, yeah, so very interesting. Okay, do we have any other questions from the audience?
Maybe just one small, maybe stupid, but I hope not, question. So as for non-transient events, I suppose the one cosmological event which we could bet the most to detect will be the gravitational microwave background, I suppose.
Yeah, though there's a, so here that also has a free parameter, and the free parameter is the temperature of reheating. And so this blue curve here is shown for the maximal reheating temperature allowed by the CMB constraints, meaning that the current constraints on the tensor scalar ratio. If the reheating temperature is much lower, then this blue curve will go down. So you're right, this is a source which is kind of not a new physics source in the sense that this is kind of guaranteed to be there, but there's a free parameter in its amplitude. But again, the other way around, once you manage to probe down here, right, you will be putting an independent bound on the energy scale of reheating and on the energy scale of inflation.
Yeah, I was just wondering because, well, as for inflation, there are many different models, and there's like not one single which we hope to observe like 100%, but at least for me, the cosmic gravitational microwave background sounds like the most reasonable which we should detect. So yeah.
Yeah,
Okay,
yeah, I agree. There's also another one which is not shown here. It's actually an astrophysical one, and that is that there might be from neutron star mergers, depending on the parameters of the QCD phase transition, there might be megahertz gravitational waves as remnants from neutron star mergers. So again, it's not guaranteed because it depends on stuff about QCD that we don't know. But if you probe this, you would be probing the QCD phase diagram.
That sounds promising. Okay, thank you.
Okay. Does anyone have any other question? If not, then let's thank Valerie again. Thank you very much.
Yeah,
nice.
Thank you for opening this field to us. So we learned something new, and it sounds really inspiring.
Yeah, thank you, and thank you for all your questions. I really enjoyed this.
Thank you very much. Yeah, so then have a nice day.
Bye-bye.
Bye. Thank you.